So how's everybody doing? So while they grab my laptop from the other lab, what I want to talk to you about today is the ability to look at taking a problem that someone provides to you, and that is whether you're in the medical field or if you're in the engineering field, you're going to start creating something based on a problem. And so the problem that we faced early on was the fact that today we operate on animal hearts in cardiac surgery to train the surgeons on how to repair valves. So take a step back for a minute. You've got 4 valves in your heart. Your heart's divided into 2 chambers. There's a left side and a right side. And the left side of your heart is more important because it pumps oxygenated blood throughout your body. So when your left ventricle squeezes, the blood should go in one direction, and that's into the aortic valve and up through the aorta, and through the ascending aorta into the arch, it goes to the brain, and then the descending aorta down to your abdomen and out through the rest of your organs. And that's the path that it travels. And in the process of traveling that path, your brain and your body gets oxygenated blood. So one way to think about this, of the importance of the left side of your heart, is to think about, well, how long can my body survive without water, without food? About 3 weeks. How long can it survive without water? About 3 to 5 days. How long can it survive without oxygen? About 3 to 5 minutes. And since the left side pumps oxygenated blood, it is critical that not only does it function properly so that the rest of your body gets oxygenated blood, but we can't afford to have it leak. We can't afford to have the mitral valve leak or the aortic valve leak. So one of the things that we did was we started with the problem. So the problem was, number one, we can't bring animal hearts, and so we used to work with porcine model hearts, which are pigs. So they recover these hearts, they ship them frozen, we take them into the operating room, and we train the surgeons on how to translate their open skills. So what they normally would do is go crack your chest using a saw, spread your ribs, and go to work on a bad valve. And as you can imagine, that's hard to recover from. It takes about 8 to 9 days to be in the hospital and about 3 to 6 months for you to recover at home, and it's quite painful. But that's the gold standard. In other words, that's the number one way that is currently being used to get access to your heart and fix your valve. And so when we started to use the animal models, because the tissue is real, we had the best possible training from it. One of the things that we found out as hospitals became penalized for having things like hospital-acquired infections and penalized by the Center for Medicare and Medicaid, we had to find other ways to train the doctors because they said you can no longer bring animal tissue into the hospital. But the current models were made out of latex, and latex is not a good replicant for tissue. For heart tissue, which is muscular, it's not good for skin. It creates a problem. And so perfect, thank you very much. So one of the challenges that we found was, we found that we had to, number one, create a new model that could be used such that we could get the same effect from training as, I could just shut that down, the same exact effect from training with a synthetic model as we could with a real model. And so we spent, unfortunately, it was about 2 years, and we're going to show you what that process looked like from an engineering perspective. Now, what's my background? So I started out at West Point in the life sciences division. I ended up branching armor because I'm a little twisted that way. I like a lot of action, and absolutely enjoyed it. And one of the things that I found in the military was that you were constantly being faced with challenges, and those challenges you had to overcome by problem solving. So a chance to use the scientific method was great. And so what I'm going to do is locate our model for you to take a look at. So what we did is we found a company inadvertently called LifeLike Biotissue. And that company had designed a tissue that they call that's made from a hydrogel. So it was a PhD, his name is Leo Millen, and he had created this material that when we saw it, it just was like nothing else we'd seen before. It was made primarily from water, and when you felt the tissue, literally, it would feel as if you were holding a real mitral valve or a real human or animal heart or valve in your hands. Even to this day, when I feel it, it makes me feel as if my hands, I should have gloves on. That's how realistic it is. And so it's accurately named LifeLike Biotissue. And so we went through this process to create something that didn't exist to solve a problem. So you're going to start with a problem, you're going to define that problem, and then you're going to go through this process. So the first thing that we took a look at was, what are the types of problems or pathologies do we want to be able to have the surgeons practice? And so what you see here is P2 flail, so there's parts of the valve that are named P1, P2, P3 from left to right. There's tissue that can prolapse or get stretched out. So when your valve tissue gets stretched out, imagine, any of you ever seen a balloon that's been overstretched? And then it starts to have an area that's much weaker and you know it's going to burst there? Well, your valve tissue can get stretched out the same way. And when it gets stretched out, it's not effective. It can leak. Sometimes there's a split or a cleft that shouldn't be between two leaflets, and now you have a problem. And there's times, this happened actually to a friend of mine who played basketball at the University of Florida. He had been playing for a while, about 30 years old. He went out to play basketball. It was hot. And then partway through, he felt something in his chest and couldn't describe it. Went to see the cardiologist, and sure enough, one of the cords that's attached to a leaflet, like a parachute, had been torn. And so that is something that the surgeons will repair frequently as well. And then annular dilatation. So if you look at the back of the room, what you're going to see is a valve. That door is a valve. And both sides of the door, so both of those doors, are considered to be leaflets. So you can open one side and keep one side closed. Imagine the door frame, if it were to stretch out another 6 inches on either side, there would be a gap in the center of the door, right? So what would go through that? Air would go through that, sound would go through that, and it would create a problem. So those types of things, annular dilatation inside your valve, is the same exact problem where the frame of the what's called the annulus, the frame of that valve stretches out. And now blood can go in the wrong direction. When blood's going in the wrong direction, it's not going to the brain and it's not going to the body, and that's a problem. So what are the effects when you're not getting enough oxygen? Fatigue. I mean, you could walk from 20 feet and feel like you ran a marathon. You'd have to sit down. You could pass out from climbing half a flight of stairs. And so this is how these people live that have valve disease. So we looked at these pathologies because we wanted to have the surgeons train on these. Then we took a look at the anatomy. So what does a typical anatomy look like? We had to identify where the anatomy is located and then determine how would we get to it, and then from there figure out, well, what shape is it going to be in when we get access to it so that we can create something that's anatomically correct. And so we started with the real-life model. The next thing that we did was we wanted to highlight certain parts of the anatomy that we would not necessarily need to model right up front because, number one, it might take too long or cost may be an issue. Because if we're trying to, remember, we're trying to go back and fix these problems. These problems are all problems of the valve itself, not for the chamber in which the valve sits, which is the atrium, and then also the valve separates the atrium from the ventricle. So we wanted to be able to fix the problems, and these problems that we see here are valve problems, not atrium problems. And so we started there. And then the next thing that we looked at is, okay, if we position this valve in relationship to the right perspective. So when we say right lateral perspective, when they do a minimally invasive valve operation, they're going to go through your right chest. Now, I realize that the mitral valve sits in your left ventricle, but your heart doesn't sit left and right in your chest. It actually sits anterior, posterior. So your left atrium is actually closer to your spine than it is to the front of your chest. So as a result of that being the heart being rotated and not how we think it is, but in real life it sits this way, we had to create the shape of the valve such that when the surgeon opens the left atrium, he or she is looking right at the valve in its normal state. And then that would be what they're used to seeing. We had to replicate that. We also did an analysis of, and we ran through a couple of different models, what could we create that was reusable to keep the cost low, because in the end, we're still trying to train the surgeons to become better, right? We're trying to translate their open skills into robotic skills or minimally invasive. So we had to look at, so what can we do? What pieces of the anatomy did we have to absolutely have, or what pieces could we make reusable? Because at the end of the day, if what we're trying to use as a training model is too expensive, no one will buy it. So we have to find the right thing for the market as well. And then we had to look at if we could create something to replicate, and what you see here is a mechanical replication of what the valve would be with a holder that we could design that would position the parts of the valve here, which is the annulus, the leaflets right in the center, and these chordae tendineae and the papillary muscles. We had to come up with a holder or a mount that would enable us to put the valve in place such that all of the anatomy would be anatomically correct. Because if it's not correct, we're not going to get the training effect out of it. So this is what we came up with initially. And we wanted to be able to create something that would very easily be put in place. We can't take 10 minutes to set this up. A typical pig heart is shipped frozen and takes about 30 minutes to thaw. So imagine you're trying to train, you got to wait 30 minutes. Then there's a host of other challenges with it. You have to position it, that takes about 5 to 10 minutes. And then at the end of the training session, you have to get rid of it, and it's biological waste. So it has to go in a special bag and has to go to a special container at that hospital, and that creates a problem for cost because biological waste is a lot more costly than your typical medical waste. And so all of these things resulted in the surgical teams taking much longer to prepare for training session than to conduct and then clean up. With the LifeLike Biotissue, we could set up in about 2 minutes, and if we had to stop practicing because the surgeon was on call or they were called to an emergency, we could break down in about 3 or 4 minutes and put the LifeLike Biotissue model back into a bag with a few drops of water and come back next week or next month. So we knew that the LifeLike Biotissue was effective that way. So some of the other things that we had to do is we had to look at real life. So what you're looking at, hopefully that's not too disgusting for the engineers here. What we had to look at is real life. And what you're seeing on the left-hand side is actually the mitral valve itself. And to show you how we redesigned it, you can see the difference between this light area and this dark area right here. That's the annulus. And if you look back at the door once again, the annulus is the door frame. So that's the annulus or the frame of the valve. Right here is the anterior leaflet, so it forms like a smile. The posterior leaflets are down here. And so what we did is we created a simple model in clay just to see what the relationships between the anterior and posterior leaflets. In addition to that, we had to look at, we had to create something that was diseased. We can't create a perfect valve because we're trying to fix something or train doctors to fix something that's not working properly. So we had to look at it and then exaggerate those things as well. So we looked at some other drawings of tissue from some of the different clinicals to let us know where are all the papillary muscles. So once again, anterior leaflet, posterior leaflet 1, posterior leaflet 2, and which is the center. That's the leaflet that has the most problems typically when a valve goes bad. And then posterior, or what they call a posterior scallop, P3. So P1, P2, P3, and this is all the anterior leaflet. But you notice how many cords are attached to the papillary muscles here? We determined that it was going to be far too expensive to have all of those cords attached accurately. when really all we needed was a couple of cords to be attached to be able to replicate the live tissue and to get the training effect from it. So we took a look at also some existing models that were made out of latex, and we studied some additional things like the left atrial appendage, which is a critical structure that enables the heart to store a little bit, or the left atrium to store a little bit more blood, but it can become a problem if the patient has arrhythmia and the blood stays there. So we wanted to add something to that, the secondary model of the atrium there. We had to look at some of the grooves to make sure that we had, in the Sondergaard's groove, or Waterston's groove is where they make the incision when they get access to the left atrium. We had to know where that was and model it accurately. And then we had to find a way to determine how would we connect a valve that was made separately to an atrium in such a way that the two pieces fit together realistically enough for the surgeon to get the training component from that. And in addition to the surgeon being trained, we're also training the patient side assistant. So we looked through and went through a couple of designs. We looked at, we can't replicate the entire left atrium because that would be way too expensive. So what could we get away with that would still give a good training effect? And we took some measurements. We also had to understand, and this is one of the key things with problem solving, is what kind of needles are they going to be using? Because what they end up doing is affixing what they call an annuloplasty band. So if you look at the valve or the door in the back of the room, if we had to reinforce that frame, we'd have to bolster it with some additional wood or metal so that I could support the weight of heavier doors, right? We have to do the same thing inside the heart. And we use an annuloplasty band that enables us to not only bring a oversized or a stretched out annulus, a stretched out door frame, and bring it down to the right size that it should be before it's stretched out, but also enable us to reinforce the tissue too. So we also need to know how big the needles were, and when they drove those needles into the annulus, we didn't want to have the needles hitting the frame of the cup or the holder, because you don't have plastic in your heart. You don't have metal in your heart. So it can't be so small enough so that the needle will hit it. We had to make the tissue thick enough so the needle could go completely through the annulus and come out and not create a training problem that never would happen in real life. And so we continued to design it very crudely, but we started to refine a design here. And what happened is, what you're looking at is they took some of the clay models that we created and scanned them and started to refine them inside of a 3D modeling tool where they could run a different series of tests with it. And then finally, as we looked at it from both sides, that's one of the things you can't do inside of a human heart, is you can't look at the valve from both sides. So we really can't get the best measurements from both sides. So what we used was, we were able to look at the models using a 3D transesophageal echo. So all that is they use sound to look at a soft tissue structure, and they can map it and model it in 3D. And so we had to look at it. We were able to turn the heart around and look from the inside of the heart out, or the inside of the ventricle through the valve, and we were able to model it this way, which is very effective. And then we came up with this design that only had a couple of cords attached to it. And then we went to work on the holder, because you can have a great tissue model, but if you can't secure it such that they can drive needles through it with a robot or with handheld instruments, then you really haven't created anything. So it has to be a combination of those two things, the valve and then the holder. And then the holder has to replicate the ventricle good enough to get the training effect that we need. And so we designed this in two parts. We designed a couple of, one out of metal and one out of plastic, and we had it two different companies that were working with us at the time. During this time, I'm doing WebExes with the company in Canada called LifeLike Biotissue. We also have a doctor that's working with us from the UK, which is a time difference as well, and also a surgeon in California. And we were all collaborating. And so over the process of 2 years, this model just continued to get better and better. And we took some simulations and positioned the clay image to determine how would everything fit spatially. So we created a 1-to-1 size model out of clay and continued to work with that. So they finally sent back, and this is what we thought was pretty cool, they finally sent back their idea. Now, I love engineers, I really do. And we absolutely need them to help us determine and design these things. But there's a problem that I have with engineers. They're always too perfect with the designs that they create. And when you have a diseased valve, it's not perfect. So I would send them imperfect designs based on true pathology, and they would send me these most exquisitely designed, perfect valves every time. And so, because there's something about an engineer that they don't want to create something with a defect that goes against your whole nature of creating something. You want to create something that's perfect, that works. Well, we're asking you to create something that's not perfect, that's diseased, that's a problem. And so that elongated the problem, but it was a good learning experience. I had to be very, very clear with them, as you can see from these images, even more clear. And what ended up happening was they still made a model that had some extra tissue, but that was no big deal because we just cut the tissue out. So that was the process that we went through. And so what has happened with it? So let's take a look at one of these videos. And I know you're not in the medical field, so we're going to show you just a training video. I promise there's no blood in this. But I wanted to show you what it looked like in a video of, or these some of the images that we were using. One of the things we noticed about this particular tissue is that it could be, the density of the material, the hydrogel, could be changed and altered depending on what you were trying to do. So there's parts of the valve that are more dense. What people don't realize is that inside your heart there is a fibrous skeleton, and the annulus is part of that fibrous skeleton for both your mitral valve and your tricuspid valve. And a surgeon had showed me that, actually, and it was an amazing thing to feel this different density of material in the same valve, because you don't ever get a chance to see that. So one of the things that we did as we were modeling this is how we had to figure out how do we place the cords, because the cords are of a denser material and they don't stretch as much, and they shouldn't. When they do stretch, it's usually permanently, and they elongate. And so we looked at a couple of different models, and what we actually did use was suture. So we embedded suture into the LifeLike material, which is a lot more elastic, and that gave us a better replication of the human mitral valve model. And so it was very valuable for us to try different types of materials to make that happen. Let's see if I can locate that other video to show you. What we ended up having to do is we ended up at the UPMC Passavant Hospital. We tried, so we had our client is University of Pittsburgh Medical Center. They've got about 23 hospitals. We started at Presbyterian, and we built a solid robotic cardiac program there with Dr. Badwar and Dr. Way. We were able to bring in pig hearts to train. We even used cadavers. It's a school, so they actually train medical school students there too. No problem at all. We'd bring these animal hearts and the cadavers right into the operating room, and then practice, and we were able to get them up to speed quickly. Same hospital system, 30 minutes away, UPMC Passavant. They would not allow us to bring in animal hearts, and we were working with another valve surgeon. So that created a problem for us. But because we had the LifeLike Biotissue model, we ended up training the first surgeon in our experience where we never used we only used synthetic models to train the team. And they did their first case, and they performed just as well as the teams that we trained using animal hearts. And so the lesson that we learned across this process was a series of lessons, actually. Number one, how to integrate the problem from the surgeon's perspective. From our perspective as a consultant, we had to work together with the engineers and collaborate very closely. And while the process took 2 years, and it wasn't because of anything more than travel schedules, because sometimes we wouldn't be able to work with the two surgeons until after a month had passed. So it was just access and being busy and their schedules, et cetera. What we found was that the closer and the better communication that we had, the clearer that we could provide the pictures. So we would go out of our way to create clear pictures of what needed to be removed. And while it was painful on our side, it helped the engineers understand exactly what we were looking for. So it helped us to communicate better with them. Then they started to figure out more of what we needed. And as we continued to talk and develop that joint language together, they were able to find the solution that we were trying to illustrate and create a model that would work for us very well. And then they sent us a couple of prototypes. And the prototypes that they sent were incredible, but they still needed some more work. I remember taking one of the prototypes for the holder and providing that to a machine shop where a friend of mine works, and had him cut additional segments out so the surgeon could drive a needle and not hit anything that's not inside the heart, a plastic sidewall of the holder, for example. Can't afford to do that because you don't have one of those in your heart, and that just takes away from the training experience. And so we improved our communication, learned how to communicate better through imaging, so we'd have to draw a lot more. We went through an iterative process such that if something was working well, we let them know what was working well. We sent it back to them. They continued to refine it until we got to a model that we can use and we use actually today. So we've created a LifeLike Biotissue mitral valve model that is diseased. It has multiple pathologies or multiple problems wrong with it. And we're using it now, and we use it at UPMC Passavant with Dr. Chris Cook, where we trained him and his team completely on a synthetic model. Never got a chance to use an animal heart in the operating room because they would not allow it, and yet his team performed extremely well. So we are now proving that you can use a completely synthetic training pathway to train surgeons on how to repair mitral valve using a robot. And once again, I want to make sure I say that properly. We're training them to translate their skills from open surgery into robotic surgery. That's it. So what does that mean? Well, you can all eat with a fork, but remember that first time that you used chopsticks? A little clumsy until you figured out how to maneuver your fingers such that you could use both at the same time. You're eating the same food, the goal is the same, to get it into your mouth and down your throat, right? But two different tools. So we are helping them learn how to use a robotic system as a tool to translate what they've been doing with these hands with something that's as thin as this, and working inside the heart to fix a bad valve using a synthetic model. And so it was a great experience for me. I wish it wasn't as long as it was, but I learned a lot about collaborating with engineers and how to learn their language, and then they learned how to learn our language. And then we found this common method of communicating such that at the end of the day, we solved our problem, which was to create a synthetic model that had a series of pathologies or problems that the doctors could use to practice, so that if they ever needed to operate on you or your family members, they'd be able to do so easily with confidence that they can repair those pathologies that I showed you easily, efficiently, such that you or your family member would have a good outcome. So I had a couple of those models with me this morning, and I think someone liked them so much that they're taking them home with them. So I don't have one that I could pass around. Plus, normally, as I said, when you feel it, what you're feeling is water, but when you feel it, it actually feels like someone has cut a human valve out and has the same, absolutely the same feeling. Now, I haven't felt human valves, I've felt animal valves, and they're very, very similar. So that concludes my briefing. Does anybody have any questions about the process, what we did, or go ahead. We had synthetic, we had 3D models of it. I'm looking at, and it was designed with 3 screws. You can see the little area here in which we secured the papillary muscles. These 3 black areas right here is actually sandpaper, because we wanted to create an area in which the LifeLike Biotissue model would be secured between 2 thin, hollow plates. And so this plate would go on top. We would screw that in, and it would actually hold it in place, even with very strong movements of a needle driver to drive those needles through the tissue. Pulling and tugging that typically happen inside the heart, we were able to replicate those and secure that model in a way that the doctors were able to practice and feel the same kind of tensions that they would feel whether they were using their hands or if they were seeing that tension created by the robotic system. And that was part of making sure that we developed something that was very, very accurate. That's one of the biggest problems when you're designing something that is based on a real-life model is how realistic can you possibly make it, and materials it really comes down to what type of materials that you're using. Okay, so this is the model that we were designing. So you can see the model to the right. Placing the papillary muscles into the holder just to see how it looks. That's what the material looks like. And you can see from how it's flopping around, there's the anterior leaflets. You can even see here the suture that we used to embed into the material as cords, because we found the right suture that did not stretch at all, that gave us the type of response, the realistic response that we needed. And that's what we looked like. The engineers, unfortunately, continue to keep some of this excess tissue that is not anatomically correct. But when you got it out of the bag and you looked at it, it looked good. It just, unfortunately, wasn't correct. So we're still working with the engineers. We need them. We like working with them. But collaboration is essential, and communication is as well. So I've got a couple other videos, but they're pretty much the same thing where the doctors are pulling and tugging on it. The last thing I'll tell you is that the feedback that we got from Dr. Badwar and Dr. Wei was that our initial model, in which we used a lower density material, was too soft. So we increased the density of the hydrogel, and we sent another model, and then they said that was perfect. So they were able to dial the density, and I'm not the engineer that designed it, in such a way that it replicated human tissue more effectively and ended up creating something that we could use very, very well. And so now it's available. It's actually a product that you can get. First time I've ever done anything like that. But the good news is that use the basic scientific method. Start with a problem, define it, gather as much information as you can from the experts. You've got to get a wide range of experts that can give you the kind of information that you need to create a good model, and then start creating prototypes of that. And then you're constantly testing prototype after prototype, get your feedback, refine, then produce something, then test it in the field, refine it again, and before you know it, you've got a product that's out there. I'm not an engineer. I'm pre-med by my degree, but the simple scientific method helped us get through this process and create something that's being used today. So you can do the exact same thing, work with the clinicians that you're here at STAR. There's medical students that are here, there's engineers. Develop that collaboration now, because you could be creating, through your biomechanics, you could be creating another tissue model or something else that we'll be practicing with to make better surgeons, because the life that you save might be yours. So work hard and help us create good products. Any other questions? All right, thank you very much.